So I wanted to do a little video here on Gauss's theorem. So we've talked about this generally in class, but I wanted to go into a little more detail for you guys. So Gauss's law says the electric flux is equal to the amount of charge divided by, that's not charge, so the amount of charge Q divided by epsilon 0, where epsilon 0 is 1 over 4 pi k. Now the simplest case for this is where you have a point charge. So we assume it doesn't have any dimensions, and then around this charge you have a sphere, so it's in 3 dimensions. But of course I can only draw it in 2 dimensions here. So you have a sphere. It's not a real sphere. It's just a imaginary sphere in space. And what's going on is you have electric flux passing through this sphere. So you're going to have, let's assume this is a positively charged particle, so the electric field vectors are going to be going outward. So it's very strong, and then it gets less and it gets less as you go out, 1 over r squared in terms of the magnitude. So at some constant radius, you're going to have these electric field vectors like that all the way around, and it's going to be uniformly distributed as long as this charged particle is exactly at the center of the sphere. And so for this particular case, the flux is going to be the electric field strength. So phi, the flux, is just electric field strength times the area. So this is the surface area of the sphere. And the surface area of the sphere is 4 pi r squared. And what happens is, as you make this sphere larger and larger and larger, the electric field vector gets smaller and smaller and smaller. But the area gets larger and larger and larger, and they compensate for each other. So you have the same flux leaving any surface that is symmetrically positioned relative to the charged particle. So you can go the other direction, though, if you wanted to figure out what the electric field strength is at a particular point in space. You would have, here's the electric field strength. This is the electric field strength. So, and the area for a sphere is 4 pi r squared. So if you plug that in here, you get the flux, which is the electric field strength times 4 pi r squared is equal to Q divided by epsilon 0, or the electric field as a function of radius is going to be Q divided by 4 pi epsilon 0 r squared. Okay. Now this charge on this particle comes from so many excess electrons. Each electron is going to have a charge of negative 1.6 times 10 to the minus 19th coulombs. So, if you have a billion excess electrons at this point in space, that's going to give you a certain charge. And that charge is going to create this electric field, which is going to vary with respect inversely proportional to r squared. Now, the second case would be, what if I put something like a bigger sphere, but it's still solid? So let's see here. So what I'm going to do is I'm going to make another sphere. So it's bigger. The amount of excess charge is the same. It's just spread over more of the material. And because this is a conductive sphere, all the excess electrons go to the outside. So you could almost have the same thing happening if you, instead of having a solid sphere, if you had a hollow sphere, again, still all the electrons would go to the outside. But what we're gonna keep constant is the amount of charge, the number of excess electrons. So Q stays constant. So if Q stays constant, and the area here, this area outside of this charge is not a real area, it's just an area in space that we're using mathematically, you can see that nothing changes. So whether you have a point charge where all the electrons, excess electrons, are stuffed into one little space, or whether they are distributed out further, then the electric field at this point, this distance from the center of the charged sphere, is going to be the same no matter what. So I could continue to increase the radius, or I could put out, let's instead of having a hollow sphere, a solid sphere, let's put in a hollow sphere. So well, let me get rid of that, because I need to make sure we have a circle, not an ellipse. So let's say we now have, let me take that point charge out of the middle, and then we stick in, so this is a hollow sphere. So now there's nothing inside the sphere. There's the sphere, which has a very thin wall, and then again you have the same surface outside of this hollow shell sphere. Again, you're going to have the same number of excess electrons, which means you're going to have the same charge on this body. Again, it's going to just be distributed further out. But Coulomb's law says, Gauss's law says it doesn't matter where the charge is, it just has to be inside this sphere. At least this hollow sphere of aluminum has to be exactly symmetric to this mathematical sphere out here. So that's kind of very interesting. We can assume, we can model this as all the charge at the center. We could model it being on this hollow sphere. As long as the radius of the sphere, the actual sphere, is less than the radius of this mathematical sphere, the electric field out here stays the same. Another interesting thing you can think about is that, if I pick some point on this mathematical sphere, and I say, what's the electric field there? Well, I know from Gauss's law it's going to be equal to Q divided by 4 pi epsilon 0 r squared, where r, this r here is the radius of the mathematical sphere. But in reality, there are billions of electrons, excess electrons, that are distributed equally around this actual sphere. And each one of those charges is going to interact, is going to create an electric field associated with a charge of negative 1.6 times 10 to the minus 19 coulombs. And if you add all those individual electrons up, the total effect on this point, the electric field at this point is the same, you'll get the same answer. So this is kind of like a macro scale. You're doing this on a large scale. You're looking at the total amount of charge. Or you could look at it on a microscopic scale, which would be a crazy problem to try to solve. You could also solve it, if you think about it, if you chose a little section of the sphere and you assume that in that little section that the electrons are evenly distributed. So there is some location for that particular amount of charge. And then you could use calculus to integrate all the way around for each one of these interacting with this point in space. And that integration should end up being the same value that you get here. And it should be pointing directly perpendicular to the surface of the hollow physical sphere. So that's pretty cool. I don't know if there's, I've looked for mathematical ways, proofs to do that, but I have not found it. Another thing is if you go to the inside of the sphere, anywhere in the center or anywhere inside these charged particles which are on the surface of this hollow sphere, the electric field inside is 0 everywhere. So no matter, even if you're very close to the inside surface or if you're at the middle, anywhere in here, the electric field is 0. And that's because there's no charge. All the charge here is outside the sphere. So there's no, if I were to draw a mathematical sphere which went to the inside of the physical sphere, the mathematical sphere would have no charge in it, so this would be 0, and therefore the electric field has to be 0. Again, I look for some kind of mathematical way of doing it, some kind of calculus way of doing it, which again this is all in 3 dimensions, which makes the problem even more difficult. But you know, if you took some arbitrary point inside here, you know, each one of these electrons is going to create an electric field. You know, in this case, this electron would have an electric field going like this, and this electron here would have an electric field going like that. And you know, the ones that are closer are going to give you a larger electric field than the ones that are further away. So if you go over here, you've got a larger distance. So this little tiny electric field going this direction is not going to be as big as the one which is closer to this wall. But there's also more electrons on this side of the sphere than there is on this side of the sphere. And again, if you did it mathematically, where you either looked at every individual electron, or you took this hollow sphere and you broke it up into individual little particle or 3-dimensional segments, and you integrated all of those electric fields together, you'd end up getting 0, which is a little mind-boggling, but it's true. Okay, so that's just a little insight into Gauss's law for this particular case, where you have a charged particle or a charged sphere inside of a larger mathematical sphere, or inside a charged sphere. Now there's one thing we didn't look at, was what would happen if you had a solid sphere. So this is solid aluminum, say, and you go to a point inside. What is the electric field at that particular point? Because you know, the question is, are there any electrons inside the inside of this, the core of this 3-dimensional sphere? And I think the answer would be no, because if this is a conducting sphere, then all of the excess charged particles get pushed to the surface. So even though this is a 3-dimensional entity, the charge is going to go to the outside, and there's not going to be any excess charge on the inside. So it's almost like a hollow sphere, even though it's not hollow, relative to the position of the electrons, and therefore the charge inside of this mathematical sphere is going to be 0, and therefore the electric field inside here is 0 as well.